sobre el pasillo de mi oficina, la oficina que está ahí.
Okay. Hay como dos personas que trabajan de eso.
¿Conoces a la persona que está allá en Morelia?
Sí, Anaí.
Anaí, exacto.
Sí, sí. Creo que es una buena cosa porque en Francia no hay este tipo de cosas por investigar, por instituto.
Ajá.
Entonces, tal vez hay como un evento en el año por toda la universidad o algo. Pero, por ejemplo, en Morelia es casi 2 o 3 veces por semana hay una escuela que viene.
Bueno, yo creo que... Bueno, creo que ya podemos comenzar nuestro coloquio del día de hoy. Y hoy es un placer tener a Quentin Salome.
Sí.
Ajá. Para darnos el coloquio del día de hoy. Quentin es ahorita un postdoc en el Instituto de Radio Astronomía ahí en Morelia. Este es su segundo postdoc, hizo un primer postdoc allá en Francia. Él hizo sus estudios de doctorado en el Observatorio de París. Y pues bueno, el día de hoy nos va a hablar sobre AGN feedback en jet-induced star formation in nearby radio galaxies. Así que, por favor, adelante.
Gracias. Buenos días a todos. Gracias por darme esta posibilidad de presentar mi trabajo. Porque no soy familiar de hablar de ciencia en español, voy a hablar en inglés. So, this subject is what I started during my PhD. I continue last year, and I try also to continue at the Instituto de Radioastronomía. So, I will first start with a short introduction about star formation in galaxies. So the simple scenario we have is that stars form in the molecular gas, and in particular in a giant molecular gas, so clouds that have typical mass of 10 to the 3, 10 to the 7 solar masses, and size of few parsecs to few hundred parsecs. And the global scenario is that this gas, under the effect of self-gravitation, will collapse, the temperature and density will increase, and at some points you can start nuclear fusion reaction. If you have mass of, the limited mass is about 0.08 solar masses. This is a simple scenario, but there are some effects that can affect star formation in this scenario. First is a stellar feedback. So when you have a star inside the cloud, then if it's a massive star, you can produce a strong UV radiation. This will photodissociate molecules, eat the gas. It can also blow out the gas with stellar winds, for instance. And also, for the massive stars, at the end, you have supernova explosions that will also push the gas away, and everything, all this feedback will affect the gas in different ways that can prevent part of the collapse. The stellar feedback is usually what it's invoked to explain when you look at the distribution of the galaxies in terms of luminosity. The observations present a lake compared with the theory from the lambda CDM models, which this difference is usually explained with lower star formation than expected. And for this low mass galaxies, it's often invoked stellar feedback. You can also have shocks and turbulence that will inject energy in the gas at scales of about 100 parsecs, so the scale of the cloud. And with the turbulence case, this energy will dissipate at a smaller scale, but will affect smaller scales and also the collapse. Now, on this plot here, you can see a lake also at high mass for high mass galaxies, and this cannot be explained by stellar feedback alone. So for this, we invoked AGN feedback. So quickly, an AGN, it's an object that is formed around the central supermassive black hole of a galaxy. The black hole is surrounded by an accretion disk. So you accrete matter, and while it's accreting matter, it will also emit energy. There is two modes. First, the radiative mode, so most of the energy will be dissipated in radiation. This is the case for quasar, for instance. And also in the form of kinetic energy with jets of particles, relativistic particles. And those jets are observed in general in a radio. And this is why we talk about radio galaxies. So what I observe is not directly the AGN feedback. I observe what we called the jet-induced star formation. So if we look at radio galaxies, there is two main kinds of radio galaxies. First, the BCGs. So it's a very massive elliptical galaxies at the center of a galaxy cluster. Here, for instance, it's Perseus A at the center. And on this image in X-rays, we have the jet here that create two cavities in the hot gas. So in this case, one possible explanation is that the jet push the hot gas, creating these cavities, and also may cool the gas in these cavities that will then may fall down to the galaxy. But I won't talk about this today. I will talk about another kind of radio galaxies. It's isolated galaxies. So here, for instance, NGC 541. So the galaxy is here. You have the radio jet here, and the jet encounter some gas. Here it's H1 gas in blue, and in clear blue here it's H-alpha emission, which is supposedly associated with star formation. So I focus on this kind of object where the radio jet, while interacting with the gas, may trigger star formation. First study we did was to observe NGC 541 here and this star formation region, which is called the Minkowski's object, at about 20 kiloparsecs away, and another galaxy where there is a spot of H-alpha emission at 70 kiloparsecs. So for this, we use the 30-meter telescope, which is, as the name says, a 30-meter millimeter antenna, which is located in the Sierra Nevada, in the south of Spain, to observe the CO gas in two transitions, CO120, CO221 at the same time. The circle here represents the different the beams of the antenna for the CO120 and CO221. And when we So quickly, first summary on how to observe the gas. There's three main methods. The first one is to observe the H1 hyperfine structure. So this is just a quantum mechanic effect of the spin-orbit interaction between the nucleus and the electron of the hydrogen atom, which is observed at 21 centimeters. So this will trace the atomic gas. Another possibility is the thermal emission of dust in infrared, because dust and gas are mixed together. So
by observing the dust and assuming a gas-to-dust ratio, we can determine the amount of cold gas. This method is very interesting as well, but you cannot differentiate between the atomic and molecular gas. And to observe the molecular gas, basically, we observe molecular line emissions. So at school, at the university, we learned that an atom has different electronic state. Then for molecules, because you have several atoms, you can also have emission produced by the rotation of the molecules, which is observed at microwave emission, or the vibration of the molecule, which produce also different levels in the infrared. So basically, you have the electronic state. Each state is divided in several vibrational transition, and each vibrational transition is divided in rotational one. In the ISM, H2 is the most abundant molecule, but there is no dipole moment. So we cannot observe the rotation in the cold gas because we need energy of about 500 K. This is why we use CO, which is the second most abundant molecules. So when we use CO120, CO221 in different position here, and when we compare with the H-alpha emission, or in the case of the two central galaxies here, the far-infrared emission as well, we can derive a star formation rate. So more or less the mass of stars that are produced per year. And when we plot the surface density of the star formation rate as a function of the surface density of the molecular gas, we found that the two host galaxies of the radio AGN here are below this trend in contours that are found for nearby spiral galaxies, while for these two central region here, star forming region here, we have only upper limit that indicate we are above this trend here. What it means is that those two host galaxies here are less efficient than classical typical spiral to form stars, while the two other here are more efficient. To give an idea, here, this dashed line here are lines of constant molecular depletion time, which is the typical time that need the galaxy to consume all the gas with the present star formation rate. So the higher you are, the more efficient is the star formation. So this study is very interesting, but now we want to understand the details, because here, basically, we don't resolve at all the star formation region. So we focus on Centaurus A. Centaurus A is nearby, quite close to us. It's only less than 4 megaparsec. So this is a very famous picture where you have the galaxy here, which is in between spiral and elliptical galaxy, and radio jet here. Why this galaxy is interesting is also because, so here you have the central galaxy, and around the galaxy there is shells of atomic gas that are located here. For instance, it's about 12, 15 kiloparsec, the same here. And those shells are were possibly produced by a past merger event. This one here? This structure, it's also arcs, and this has stellar shells that are also an indication of a past merger event. Basically, when you have a merger between two galaxies, the stars just pass through each other without interacting, and basically they form in shells that will oscillate in the gravitational potential of the galaxy. Now, if I combine both images, here you have Centaurus A, the H1 shell, one of the H1 shell here, and the radio jet. So this shell is in the direction of the jet. Also, along the jet, there is two filaments seen in optical with young stellar population and H-alpha emission. And this one seems to be at the interaction between the jet and the H1 cloud, which seems to indicate a possible jet-induced star formation. So here is the zoom in. The image here is far UV emission, which is a tracer of recent star formation. And also, with the same morphology, there is young stellar clusters, which indicate a recent star formation and possibly triggered by the jet. There is also dust emission from air shell in a white contour here. The black contour still is a H1 shell. So if there is molecular dust emission, we can expect to observe molecules and molecular gas. In 2000, Charmantaris et al. Made observation of the CO in the two shells aligned with the radio jet, as well as inside this shell. In the two shells here, they have clear detection of both CO120 and CO221. But in these shells here, they did not detect the CO. So their conclusions are that because they are aligned with the jet, the molecules they observe, the molecular gas, could be a result of the interaction between the jet and the atomic shells. Now, to go deeper and go back to the northern shell, here the red square is an area mapped by Charmantaris et al. With the CEST in the past. And now with Apex, which is located in Chile, very nearby to ALMA, we map all the far UV filament as well as this strong dust emission peak. So basically, we covered three kinds of regions. One inside the H1 cloud, one which is at the edge of the cloud, so supposedly where you can have the interaction with the jet, and one which is completely outside, with only far UV emission, or in this case, with only dust emission. And on this dust emission map, I represented all the spectra we observed. So we detected CO in almost all the positions we observed, and we found this surprisingly bright CO emission in this region, which is completely outside the H1 cloud. We first compare with the far UV, a combination of far UV and dust emission to derive the star formation rate. And basically, we found for the full filaments, we found a star formation rate of about 10⁻³ solar masses per year, which is quite low. It means one star, like sun-like stars, every 1,000 years. And this corresponds to a molecular depletion time of 75 giga-year, which is 5-6 times the age of the universe. And in particular, if we compare in normal spiral galaxies, is 2 giga-year, which means that the star formation rate is very inefficient, and it's very clear on this plot. So still the contour for nearby galaxies, and all or apex point here are below those contours, and at depletion time of more than 10 to the 10 years. Now, here the colors is the CO emission. We produce a map of the CO emission with still the H1 contour here. And we wanted to compare the H1 with the H2. So first, we had a small difficulty that the resolution of the VLA correspond to about 3 times the resolution of apex. So we simulated lower resolution of apex by adding several positions to determine one H2 mass. And basically what we found is that in between the central region where the ratio of the H2 to H1 mass ratio is about unity or lower than unity, then this ratio will increase to about 5 at the edge of the H1 shell. And here we found something which is about 20. So we have only upper limit or low values because we are completely outside the H1. But we clearly see a gradient of this H2 to H1 mass ratio. Also, if we look in totality for all the color region, we found a ratio of 3.7, which means that the filaments, the far UV filaments, at least, are associated with gas, which is mostly molecular. And we conclude that probably there is a H1 to H2 phase transition that is triggered by the radio jet, which means that probably the H1 shells was larger in the past, and because of the interaction with the jet, this H1 gas was converted in H2 gas at the edge. When we look also at the velocity of the H1 and H2, in 2005, in a direction which is about 45 degrees, Osterlo and Morganti observed first a gradient of H1, and about at the position of the jet, they found a change in velocity, which is very important. And we observe the same in CO. So basically, we have a trend here that seems to continue with the CO bright region, and a similar change in velocity here. And we suppose that this change in velocity is produced as well by the interaction with the jet. So first, in our first study, we observed a star-forming region along a radio jet in globality. Then, with this second study, we observed scales of about 500 parsecs. And the next step was to use ALMA. So with ALMA, we map all the filaments. This corresponds to the far UV filament and the dust emission. And we observe at a resolution of about 1 arcsecond, which corresponds to about 15-20 parsec. So basically, this resolution enabled to distinguish the different molecular clouds. We use a clustering method because just like this, it's quite difficult because the signal-to-noise ratio is not the best, but we use a clustering method and a Gaussian decomposition method to extract the different clouds. So on the same image I represented, in contours are the different clouds we observe. And basically we have two main structures. One here that we call the horseshoe complex because of this horseshoe-like distribution, and the vertical filaments here, plus some isolated clouds in other positions. Now, if we compare with this is an image of the H-alpha emission, we see that the CO emission seems to follow the H-alpha emission as well. And in this region, the vertical filament here, it's also associated with young stellar clusters that are represented with black crosses. Now, we made statistical analysis about the different properties. So in each of these four histograms, so the radius, the velocity dispersion, the gas density, and the virial parameter here, which is kind of a ratio between the potential and kinetic energy. For each of them, in red, the red histogram corresponds to molecular cloud in the Milky Way. This was a study of Mivildeshan et al. 2017. The black histogram is for the full sample of clouds we have, and we separate between the horseshoe complex and in blue and the star-forming clouds in red. So on each of them, we found that basically we have the same properties or similar properties inside the molecular cloud of the filaments of Centaurus A and in the Milky Way for each quantities. Even for the virial parameter, the only thing is that for the virial parameter, it's slightly higher than in the Milky Way when we look at the mean value. And also the horseshoe complex at slightly higher virial parameters than the star-forming clouds, which could indicate two different regimes of star formation, and also why we don't see young stellar cluster in this region. When we look at the Larsen relation, so here the mass as a function of the radius, the velocity dispersion as a radius, velocity dispersion as a function of mass, we found that all clouds represented by the black crosses are in agreement with the inner Milky Way, like the molecular cloud of the inner Milky Way. The problem is that the spread in radius here is very small, possibly because we miss the larger scale due to the filtering by the interferometer, which doesn't really able to conclude directly about this. But if we look at the velocity dispersion as a function of the product between the gas densities, surface density, and the radius, it appears that we have a good correlation here. So to conclude about this, basically, we found the horseshoe complex has a virial parameter of about 12 plus or minus 7, but this value of 12 is similar to the outer part of the Milky Way, where the star formation is low, which can explain why we have low star formation. While here we have a value slightly higher, but basically this value of 8 indicates that self-gravity is not strong enough. So we still have low star formation, but more star formation than above. So quickly to conclude about this different studies, we have two kinds of objects. First, the first two star-forming regions we observe. Basically, we have little molecular gas, indicated by the fact that we did not detect them with a 30-meter telescope, with high supposedly high star formation efficiency. While on the opposite, in the northern filament of Centaurus A, we have a large reservoir of molecular gas, but low star formation efficiency. But what our ALMA observation revealed is that possibly the star formation is still triggered in the filaments of Centaurus A, in the sense that without the jet, no star formation will take place at all, or very, very few. And basically that the jet induces first the formation of molecular gas that may form stars after. But we have several parameters that we can affect this result, and in particular, the star formation efficiency estimate. First problem with low metallicity effects, and also different initial parameter, for instance, the impact parameter between the jet and the gas, where the gas comes from, the age of the interaction maybe. So for this, we'll need a statistical sample to explore the parameter and try to find some trends. Also, we can observe other transition and other molecules as well, and maybe higher resolution. So I will finish with some example of what we plan to do. First, in the CO bright region we discovered is with apex in Centaurus A. We also observe CO322 and CO423, so different line of the CO. And we also have upper limit of AGN, HEO plus, 322, and the atomic carbon. And by combining with the CO120 from ALMA at higher resolution, we can derive ratio of the integrated flux of the different line with the integrated flux of the CO120. So these are the different points here. And we can fit low velocity gradient models here with Radex with different density and temperature of the gas to obtain constraint of the physical condition of the gas. So for this, I won't present more because these are very new, but it's a primary work for higher resolution observations. So this is a CO120 map of the molecular cloud we discovered with ALMA. And with ACA and ALMA, we also have a map of the CO322, not in all the region because of some technical constraint for the observations. And also in HEO plus 120, where HEO plus is often used as a tracer of denser gas. And we clearly see the same morphology between the different transitions. So for this, we will use also LVG models, but also shocks models or PDR models to give other constraints on the density of the interaction as well, the energy injection. And we also propose observation with ALMA for other transition of CO and reobserve AGN HEO plus because our previous observations were not complete. And we will do this in 3 different regions here that seems to present different characteristics. One inside the horseshoe complex, one inside this vertical filament here, and one cloud which is close to the H1 peak. Also, we propose observations in the whole complex here and this whole filament here to observe CO at higher resolution. Here we aim to observe at about 2 parsecs. And with this, we will cover, by combining these observations with AGN as well, which is a short spacing, and with a total power, we expect to cover 2 to 3 orders of magnitude. And with this, we expect to be able to observe the turbulence inside the different, the 2 complex, or also explore the Larson relation with a larger range in a radius. We also have observations of another object which presents similar characteristics, NGC 4258, which is also a nearby galaxy. In this case, it's very interesting because this is a spiral galaxy, and in this case, the jet propagates inside the disk. So basically, the interaction will take place with gas with different properties due to the gravitational potential in particular. So these are CO observations at quite similar resolution, about 30 parsec, and we can distinguish different clouds that seems to be aligned with the radio jet in that direction. And finally, one aspect we'll need to observe is the effect of low metallicity. So this is the plot I showed you at the beginning with the 2 star-forming regions and the 2 host galaxies. The Minkowski's object, we didn't detect it, but in 2017, Lassie et al. Detected CO emission, like 4 clumps with ALMA. And here, the color corresponds to the more or less to the distribution in this plot. Now, there is 2 effects that can affect this. First, the estimate of the molecular gas mass depends on the metallicity. We just apply a factor between the CO luminosity and the H2 mass, but this factor increase is the metallicity decrease. So in this case, this spot here will just move in that direction, maybe in the typical spiral contours. And also, here we observe only, we use only the H alpha emission to determine the star formation rate, sorry. And H alpha can also be affected by other process. So you can have H alpha emission which is associated with shocks only. So in that case, it means that we could have overestimated the star formation rate, and this will just propagate south. So if we have, for instance, low metallicity gas with a lot of shocks that produce the H alpha, basically this high efficiency will just convert in low star formation efficiencies. To show you how the H alpha can be affected by other than star formation, these are the H alpha emission observed with Muse by Centaurus et al. In 2015. Muse is a spectroimager. So basically, you have a cube with 2 dimensions of space and 1 dimension in a frequency or here in wavelengths with several optical line emissions. And when we use different line ratio, we can distinguish, depending on the position in this plot. In green, it's the emission lines that is associated with star formation. In blue, it's associated with either AGN ionization or shocks, and the red part is kind of a transition between the two. For instance, for the molecular cloud we observed with ALMA, I produced the same BPT diagram. They are called BPT diagram, and we have only a small fraction of H alpha emission that is produced by star formation, and a larger part produced by shocks. And if I represent the map here of this distribution of excitation, we only see one star formation region associated with molecular gas. And that's it. Thank you. And if you have any questions.
Questions? Comments? I have.
Thank you. Very cool presentation. What's the way that you are inferring the H2 masses or the molecular?
Oh, I haven't a slide like this.
See, sorry. I think you were talking about like.
Yeah. So basically, I will go back to this slide. So as I said before, the H2 is the most abundant molecules, but we cannot observe it directly for cold gas.
Yeah, that's why you use the CO.
Yeah,
okay.
Because CO is the second most abundant. Now, to derive the H2 mass, we use the CO luminosity.
Okay.
We assume the virial theorem, and basically you just have a multiplicative factor between the H2 mass and the CO.
Okay.
So it's basically the factor of 4.3 or something.
Okay.
But this factor can be affected by a metallicity effect.
What you were mentioning like 3 slides before you finished.
Yeah,
okay.
Exactly.
I was going to ask you another thing then. Can you constrain or with these observations understand how is the dependence with this?
There are several studies that observe that determine some trends of the H alpha of this alpha CO factor.
Yes.
With the metallicity. With the current observations we have, we cannot constrain that.
Okay.
One possibility is to use optical line ratios. So at the end. So I said with optical lines we can constrain the excitation, but with other ratios we can have an estimate of the oxygen abundant, which is more or less a metallicity. So we did it for Centaurus A, and we found a metallicity which is slightly subsolar. So it doesn't affect so much. But for this object here, we don't have this kind of observations. Okay. So we propose with Muse as well to observe Minkowski's object. Because the object is not that big, so we can do it with one field of view. And so we just wait to know.
I was wondering if you could constrain. I've read that if you go to lower metallicity, this factor tends to
will increase. Yeah, and
but I see that also excitation,
turbulence. Yes, this is why we propose to observe with Muse to constrain both the metallicity and excitation.
It would be very cool.
Because if we are at a solar metallicity, we can still have the excitation that will go down here. So,
more questions?
Thank you for the nice talk. I have one question. In the case of Centaurus A, in the area where you resolve the molecular clouds with ALMA, is this material that has cooled from the jet that has come from Centaurus A, or is where the jet is interacting with another stellar system or galaxy?
Yeah. So the filaments are here more or less.
Mm-hmm.
So we assume, maybe it's a strong assumption, that the molecular gas comes directly from this H1 gas first.
That was there.
Yeah, it was H1 gas there that convert into H2. Now, for those 3 shells here, the current idea is that this gas comes from a small galaxy that interacted with and merged with Centaurus A. And basically, it was gas that was stripped out and formed shells like this.
Yeah, I was asking that because when you compare the properties of the clouds with the Milky Way clouds, you said that they were similar, but really they were within the range of the molecular of the properties of the molecular clouds in the Milky Way, but you are lacking, for example, very large ones. So there are significant differences. They are just within the range of the parameters of the molecular clouds in the Milky Way.
Yeah, so we say that the properties are very similar, but if we look here in particular in the size, we see first that we don't observe
very small ones.
Small ones.
This is ones.
Because of some resolution effects. And the larger one here, we need to explore this, but the problem is that with ALMA, or any kind of interferometer, we are sensitive only to a range of scales. So the normal resolution, but we also filter the larger scale. This is why we need what we call the short spacing. So this will be made with ACA. So here you have ALMA, it's a network of 12-meter antennas, and there is a more compact array, which is called ACA, and we need to combine both sets of observations. The thing is that this is not tricky in that case because ACA has smaller antennas, so we don't observe. We cover the same region, but not exactly the same position in the sky. So we are still working on this combination. And we expect with ACA to have access to larger scale and maybe either to observe diffuse emission or the outskirts of the molecular cloud that are not filtered, but maybe at low signal to noise ratio. So this is the next step we plan to do, and also why we ask for higher resolution.
Thank you.
And maybe by exploring the Larson relation, we'll see some difference from this. And
more questions? Well, I have a comment. So if you come back to the Larson's relation, so so it's something related with what Chucha asked, and I think it makes sense that you're looking to. I mean, you're seeing different physical processes, no? So, and I don't know, probably to me it makes sense that you are seeing basically high density molecular clouds, no? So they are small for the masses that they have. They have smaller sizes, no? They are more dense. So when you look to when you compare it with the molecular clouds of the Milky Way, the processes for the creation of the molecular clouds in the Milky Way was something more gravitational, no?
Yeah,
More for
sure.
process gravitational. And here you are seeing a different process. So you are seeing the difference between nature and nurture.
Yeah,
basically.
Here, basically, our idea is that probably the jet inject energy and turbulence that enable to form the star formation. But probably this turbulence is quite strong and still sustains the collapse at larger scale. So this is a possibility. Also, the conditions are completely different because here we don't know the size, the depth of the H1 cloud, but in the Milky Way you have the pressure from the disk as well.
Right.
So
yeah, and that's why I'm not so very surprised that you don't recover the Koenig-Schmidt law when you compare with normal galaxies. No?
The thing is that so if I go back here, here there is also another possibility, let's say, is that basically the Koenig-Schmidt below about 1 kiloparsec, star formation and the molecular gas start to be especially incoherent. You can distinguish them. And because here we focus on the molecular gas and not on the star formation rate, maybe this can be an effect. But in our case of Centaurus A, we, with our current knowledge, we suppose that the Koenig-Schmidt cannot work with this kind of object, and that the gas density is not a good tracer of star formation compared with galaxies.
Right. Okay.
But this is a tool we have currently, and to compare with something, we need to have idea.
Okay, more questions? If not, let's thank again Quentin. And we have the after parties to talk more about radio jet-induced star formation. Gracias.